All right, so we started section 9.4 on permutations and combinations last time. I want to do a real quick run through to remind you of the different ways we have of counting, like counting strategies. So the first counting strategy that we had is called the fundamental principle of counting. So when the fundamental principle of counting happens, it means that there's different things that we're doing in some kind of an order, and the order matters as to what's going on, right? So like if you're putting on an outfit, you can't put your shirt on your bottom of your half of your body, right? So the order in which you're doing it matters. So that's what happens when we're looking at the fundamental principle of counting is there's an order that's mattering in the process, and there's these distinctly different activities that we're doing. Permutations of like objects. Like objects are things where some portion of what you're considering are alike, and they're alike in some fashion. Maybe they're alike in color. Maybe they're alike in your classification, right? So we're going to see one, I think, today that's got your classification that's different. Are you a freshman, a sophomore, a junior, and a senior? So you're alike in that fashion. So they're like in some way that you're considering as being like objects. And so this is this one. We had permutation of unlike objects. So unlike objects are exactly that. They're distinctively different from one another. And so we have yet another formula or way of processing through that. The difference that's usually people get confused between this one and the next one. The difference between permutation of unlike objects and the difference and combinations is whether or not the order matters. So when we do permutation of unlike objects, the order matters. And the formula is quite similar to the combination formula where the order does not matter. And so we saw things where we were looking at the different orderings not being a relevant feature to what's going on. Another one that I failed to mention last time, though we saw sort of an example of it, is the idea that if you're creating an ordering of people, we talked about like finishing in a race, like first, second, third. But also if you were doing something where you were looking at a group of students and they had specific roles to fulfill on like a committee, like president, secretary, treasurer, that kind of stuff. The roles that they're filling is different, so it would be different if you got elected to the president spot than you got elected to the secretary spot. Y'all know what I'm saying? That'd be permutation of unlike objects because the roles in which you were serving, the order of the location where you are in that grouping matters. Whereas if you were doing combination and you looked at something that was that one, it would be something like a committee. You're all elected to a committee, and once you're on that committee, then maybe roles are assigned or whatever, but you weren't elected to a specific role. You were just elected to be put on a committee. So it doesn't matter whether you were elected first or third, you're still on the committee. So the ordering of it doesn't matter. So that's another one that we had not encountered or talked about last time. So we're going to take a look as we go through example 6 and on, and we have to make the decision when we look at this, do we have fundamental principle of counting, permutation of like objects, permutation of unlike objects, or combination. And sometimes there's more than one way to do a problem, sometimes, okay? So here's our first example for today, example 6. We have phone numbers in a business. This used to be really common. In fact, even on campus, every prefix for our campus is 585. I don't know if you guys know that. It's 405 and then 585. And then the last 4 numbers are different. So that's what you're seeing present in this particular problem. So all the numbers in this business are 405, 767, and then they've got 4 numbers after it. We're going to decide how many different phone numbers are possible. So, what do you see this problem as being of our 4 types? The order does matter, which means it eliminates combination. So sometimes if we can't think of which one it is, we can at least eliminate something it's not. It's definitely not a combination. The order definitely matters, right? You've probably all put in the phone number of somebody wrong before and get somebody else on the line, right? Yeah, so it's not a combination. Now we're down to 3. We've increased our probability of guessing right. No further thoughts? Okay, we should be able to eliminate one more as an obvious no. It's not going to be that one. There's an obvious elimination besides combination. That one was a good elimination. Nobody wants to talk. There's 3 other things that we could try. Which one makes no sense?
Would it be the permutation of these like objects?
Yeah, that one completely makes no sense. Each of these different 4 numbers at the end are completely different objects from one another, right? They're entered in the phone in a different order. So now we're down to 2 things. It's either permutation of unlike objects, or it's the fundamental principle of counting. So if it's permutation of unlike objects, the problem we run into with that one is that, think about our example where we were putting people winning a race or contestants in a game show, I think we had, or something like some kind of raffle. Once a person wins the raffle, they're taken out of contention, right? So if they get first place, second place, or third place, they don't get another place. Does that happen with our numbers? Think about the way phone numbers work. No. I mean, those 4 numbers at the end could be literally any of the 4 numbers. Just because I used the number 1 in the first location doesn't mean I couldn't use the number 1 in the second one, right? So that's going to eliminate the permutation of unlike objects as well. So we are going to be using the fundamental principle of counting on this one. So with the fundamental principle of counting, and you're welcome to write this down, one of the things that makes it sort of the only option in some cases, which is like this case, is that it allows repeats. With a phone number, I can repeat the numbers at the end. I'm allowed to do that. So if you had a raffle where people's names were drawn out and then put back in, it could be done with this too, right? That would be the same object. That's not usually how raffles are done. But if you had one like that, you could do that. All right, so these 4 lines right here represent my 4 X's here. They're the 4 ending digits of my number. That's what it is. How many different numbers could go in the first location? 10. And if you're counting 10, it means you're starting at 0 and going up to 9. That's why there's 10 of them, not just 9. So there's 10 different numbers that could reside in this location. How about the next one? 10. The next one? 10. And the last one? 10. So in this one, there are 10 times 10 times 10 times 10 ways this can happen. Fundamental principle of counting, so then multiply them, so you see the dots between. What number does this give me? 10,000. So this large business could support up to 10,000 different phone lines that are all different, right? That's a fairly large business. Yeah, fairly large business. So there's 10,000 numbers, or possible numbers, let's say that. Okay, ready to try another one? Okay. A worship team practices 8 songs on Wednesday night for the Sunday service. If the worship minister plans to choose only 5 of the 8 songs, in how many ways could the songs occur? This is the way music works, right? Like you practice lots of things. If you're in any musical groups on campus, this is probably what you guys do too. You practice lots of different pieces, and then when you go somewhere, you don't perform them all, right? You perform some smaller collection of them usually. So this is what's happening with this worship team. They've got a repertoire. They've practiced 8. They're only going to choose 5 on Sunday. All right. What options do we have, or what options should we eliminate as things that won't work and don't make sense?
Well, we could eliminate.
You're good, Autumn. I'm going to write down the 4 of them.
Well, we could eliminate the fundamental principle of counting because we don't want to repeat a song.
Yes, that's true, but fundamental principle of counting doesn't have to repeat.
Oh.
It doesn't have to repeat. It just is the only one that can. So if you have something that repeats, it's fundamental principle, but just because it doesn't repeat, because you're right, this one won't repeat, that wouldn't quite make sense, doesn't mean that it has to be eliminated.
Okay.
These are our 4 options.
Would you eliminate the permutation of unlike objects because the order doesn't matter?
Does the order not matter? Because that's the question. So we need to address that question because it will allow us to eliminate one of the 2, right? So if the order matters, we can eliminate combinations, and if the order doesn't matter, we can eliminate permutations. So does the order matter? Gracie says yes. Pretty strong shaking of the head. Can you give an argument as to why you believe that?
Because putting them in a different order would be a different way that the songs happen.
Right. The language here actually says how many ways. So it would be a different way if you altered the order. So what that does, though, JC, is it allows us to eliminate one of them. It's just going to allow us to eliminate combination instead of permutation. So this one's not going to work because that one, the order doesn't matter, and ours does. So we've kind of got two that we think might work. At least we haven't been able to eliminate, and we've discussed them, right? Permutation of unlike objects and fundamental principle of counting. What about permutation of like objects? Can I eliminate that one, or is that one still in the running?
Couldn't you eliminate that one because the songs would be different?
Yeah, all the songs are different. Now, if we were doing something with songs where we wanted to put them in categories, like slow song, medium pace song, loud song, soft song, then we might have to be doing that, right? But that's not how these are being structured. These are just distinctly different songs. So you're right, we can eliminate this one. The reality is the two that remain are both able to be used to solve this problem. So let's do it with one of them, and then we'll do it with the other one, and you can see how they work and that they both give you the same result, okay? So fundamental principle of counting is ones where we write down the little lines for how many we have. So how many songs are going to be sung on Sunday? 5. So I'm going to write down 5 lines, like so. How many songs do we have to choose from on our first song selection? 8. But then just like we addressed before, we're not repeating that song, which means the second song means we have 7. And then 5 and 4, right? Okay. So grab calculator if you'd like. We're going to multiply 8 down to 4.
6,720.
Okay, do I have a second on that? Yep, wonderful. So this is a perfectly valid way of doing this problem. Permutation of unlike objects works too. So as a reminder, let me write down the formula for that. It's NPR. I have n factorial on top, and I have n minus r factorial on bottom. So n is the number we have to choose from. So how many are we choosing from? 8. So I have 8 factorial on top. The denominator is the number we choose from minus the number we choose. In other words, it's how many we don't choose. So if I have 8 songs, and I'm going to choose 5 of them, how many am I not choosing? 3. So you can either write down the 8 minus 5 equals 3, or you can process through it more from a conceptual standpoint of what I'm doing in the denominator is I'm eliminating the things that are indistinguishable, right? It's indistinguishable, the 3 songs that didn't get picked. They just go in a plot of, it doesn't matter, right? It doesn't matter what order I would have done them in. I'm not doing them. So if we take a look at writing this out the way we did last time, 8, 7, 6, 5, 4, and 3 factorial over 3 factorial. What do you notice when I cancel the 3 factorials out? Yeah. I get the exact same thing, 8 down to 4 multiplied, right? Just like I did with the other process. I'm thinking about it from a different perspective, but it works as well. So in either perspective, I end up with 6,720 ways. Right? There's 6,720 ways I can do the song. All right. Example number 8 has lots of parts to it. Okay, so let's take a look at example 8. A standard 52 card deck is used. Okay? I'm going to run through some basics about a standard deck of cards, just in case you're not very familiar with them. In my house, we play lots of games, so my kids are very familiar with decks of cards, but I know that not everybody does. So jot these things down if it's important to you to have a list because you're unfamiliar. In a standard deck of cards, there are half the cards that are black and half that are red. Okay, so half of 52 is 26. There we go. 26. There's 26 blacks, 26 reds. There are 4 suits of cards. hearts and diamonds. Those are red. And then there's clubs and spades, and those are black. So if I were to take the same 52 card deck and divide it among the 4 suits, I would have 13 of each suit. So there's 13 hearts, 13 diamonds, 13 spades, and 13 clubs. All right, the number cards in a deck of cards start at 2 and go up to 10. So there's no 1. There's 2 through 10. Those are my number cards. So every suit, clubs, spades, diamonds, and hearts, has a 2 through a 10, and just one of them. And then they also have 3 face cards. Face cards are Jack, Queen, and King. You have one of each suit. And then there's another card that they all have. It's not a face card. It's not a number card. It's the ace. So you have an ace of hearts, ace of spades, ace of diamonds, ace of clubs. Depending on a game you play, it might be the top card. Okay, so a lot of gambling games, they do it that way. But it also might be the low card. And there's some gambling games that make it the low card, and there's some that actually make it both, depending on what's going on. Blackjack is one of them. Okay, so an ace sometimes gets assigned the value like 1, and sometimes it gets assigned the value that's like high, a high card like an 11 or a 13 or something like that. Okay, so everybody good on the basic structure of what we're looking at? Okay, now let's take a look at the question that's being asked, and then we're going to be making some calculations. The question says, how many different 5-card hands can be dealt? So we have 4 different things we need to decide among. Fundamental principle of counting, permutation of like objects, permutation of unlike objects, and combination. Can you either eliminate one, or do you know which one you'd need to use? We can go from either perspective. What do you think? What do you think, Emily?
Well, it says that there's 5 different 5-card hands.
Mm-hmm.
So, which one was the one where it had to be different, like each? Like once one was used, was that the fundamental principles one?
Okay, so what I think you're thinking about is the ones where we would eliminate the ability to have repeats. So we definitely eliminate the ability to have repeats here. I can't have 2 jacks of hearts, right? Like that's not a possibility. But that doesn't eliminate fundamental principle of counting. It just means that fundamental principle of counting might not be used. Fundamental principle of counting can be used when it's repeated or when it's not repeated. So it doesn't eliminate it, unfortunately. But you're right, we're not going to have a repeated card. There's one that we should be able to eliminate pretty easily. Is it combination? So combination, the order doesn't matter, right? So if you're playing a game and you're dealt 5 cards, does the order in which they're dealt matter? Anybody played Uno? Go Fish, Old Maid, among others. Usually what happens when you're playing any kind of a card game is that when you get your cards, somebody starts putting them in a different order in their hand in some way that makes sense to the game. You know what I'm saying? Okay. So, does it matter the order in which the cards are dealt? It does not matter. So, Caden's actually picked the one that we want to use. We want to use a combination because the combination is the only one where the order doesn't matter. Everything else, actually, the order matters for, in some fashion or another. Fundamental principle of counting matters in the order, right? We pick 9 things here, or we pick 10 things here, or whatever, but the order in which it matters. Permutation of unlike objects, the order matters. And it's not permutation of like objects, regardless of the order mattering, because all my objects are different. Right? Every card is uniquely different, unless I was playing a game where I had like 2 decks in it or something like that, which is not what they're describing. Okay, so we are in a combination situation for these. And that's actually true for every one of our problem 8 ones. We're going to be using combinations the whole time because we're dealing with this deck of cards. So we don't have to revisit this question along the way. So we have 52 objects because there's 52 cards. And we're going to do a combination, and we're going to choose how many of them? 5. 52C5. So the combination formula puts 52 factorial on top. That's how many you're choosing from. And then the denominator, the two pieces of the denominator are how many you're choosing and how many you're not choosing. So how many are we choosing? 5. And it doesn't matter the order. That's why we're eliminating the distinguishability of them by dividing it out. And how many are we not choosing? Subtract, guys. How many are we not choosing? Thank you so much, Kate. 47. Okay, so this is the format that we use for combinations. So we're going to write our 52 out. This is a really good example of one that if you tried to do 52 times 51 all the way down to 1, your calculator will give you an error overload, or it'll put it in scientific notation, neither of which are helpful for the problem, by the way. So we're going to definitely want to write this out and stop at the 47. And then the denominator, I have my 47, which also just gets written as 47 factorial. But then the other one has to be written out. 5, 4, 3, 2, and 1. Remember, the only way you can cancel factorials is if they match exactly, not just if they're divisible by another. So the 47 factorials cancel. That's perfectly fine. Now I need to eliminate the 5, 4, 3, 2, and the 1's automatic with things in the numerator. If you really wanted to in this one, you could multiply this numerator out, you can multiply the denominator out, and you could divide it. It would be okay. But you can also reduce it and not do as much multiplication if you'd like. So do you see something that would nicely divide out? 5 and what? 5 and 50 is a good place. Yeah, absolutely. So that gives me 10. Now what? How about the 4? What's the 4 nicely divide by? Or divide? 48 works nicely. What's 48 divided by 4? 12. Okay. How about the 3? You had a couple options.
51.
The 3 will divide 51. What is 51 divided by 3? 17. We could have also divided the 12 by the 3, if you saw that one. That'd be another choice. Last one, the 2. We got lots of choices. What do you want to divide in the 2 into?
I did the 52.
The 52. Perfect. 52. And we did this one earlier out loud as 26. So as we're taking a look at multiplication, we're multiplying 26, 17, 10, 49, and 12. What does that give us? Yep. And this is the number of hands of cards. So once upon a time, this has happened a long time ago, my husband used to watch the Poker Channel. And they would display the likelihood at people's hand. They played Texas Hold'em. That's the game that was played, which is a 5-card game where you get, I think you get 2 cards and there's a flip that has 3 cards. And so you combine your 2 cards with their 3 cards, something like that. It's been a while. But the thing that would show in the little corner of the screen when you were watching it is their probability of winning based on what their cards currently were. So as the audience member, you could watch it and you could see the math change on the screen. They're doing this math on that screen. That's what they're doing. They're finding out probabilities. Right now we're doing the counting strategies. But the counting strategy that we've got right now, this 2 million number, is how many different card hands there are. That's a huge number. 2 million? I mean, like, for real. Huge. Okay, so we're going to take that and we're going to compare it to getting certain kinds of cards dealt. So for example, on this one, letter B, we're looking at the hand that you're dealt having all diamonds. Okay, so not all the cards are diamonds, right? Not all 52 are diamonds. How many diamond cards how many diamonds are there? There's 13. So if I want all diamonds, I have to have 13 that I'm choosing from, and all 5 of the cards I'm getting have to be diamonds. Are you with me? So this is clearly going to be smaller. I mean, right? I mean, I only have 13 to pick from instead of 52 to pick from. The question is sort of like, how much smaller? Does anybody know what kind of a hand this is called when you get all of the same suit? It has a name. It's called a flush. So if you hear somebody say flush when they're talking about cards, they're talking about this, all of the cards being in the same suit. So we have 13 factorial on top. We are selecting 5 of them, which means how many are we not selecting? Yep, 8.
Oh, great, because it's a smaller.
Yes, smaller. And you can also notice that the denominators on these for combinations always add up to the numerator, right? 5 and 8 makes 13, so it's a quick one to check on. So we're going to write our 13 down to 8. So my 5, 4, 3, 2, and 1, and there's that 8. So the 8s cancel. What else do you see?
The 3 and the 4.
3 times 4 is 12, so we can cancel those out sort of in pairs. What else? Yeah, 5 and 2 make 10. So we have left 13, 11, and 9. 13 times 11 times 9, what do you get? 1,287. Now that's a lot. That's not a lot compared to the 2 million, is it? And if you wanted to know the probability that when you're playing this game that your hand is going to have all diamonds, you could take this number, 1287, and you could divide it by this number, 2,598,960. And that's the likelihood of actually getting a flush that's all diamonds. Okay? It's not big. It's very small. So this is hands as well. So let's look at another one. Oh my goodness, did I do something wrong? Oh, I did it. 3. See, this is what I wanted us to do. I just was jumping ahead of things. Oh, I was so excited. C is going to do what I just described. We're going to find the probability of actually making that happen. So we're going to have the number of ways of having all diamonds divided by the number of ways of having any hand. Which means we're going to actually take that 1287 and divide it by that 2,598,960. So you're definitely going to need a calculator to do that. It's not going to be a nice value. And we're going to write this decimal out to 4 decimal places. So what do you get? I have 5. Just have 4 something.
Do you know, so after you go 4 decimal places, do you have to round it up?
You have to round after that. So you look at the 5th one to decide if you round the 4th place. So yeah,
Okay,
it'll be
I
5.
can do that.
It's okay. So this is a small number, and if you want to sort of have a perspective in your mind, I'm not going to write on my screen, but multiply it by 100. Just multiply your value by 100 in your calculator. You should get 0.05, did you? That's the percent. 0.05%. Like almost nothing, right? It's so, so small. Almost never going to happen kind of thing. All right? Okay, let's shift gears and look at one more example. This one's a committee example. So I kind of spoiled the fun already, but do you remember what I told you about committees? The order doesn't matter on committees. So if you see anything that's talking about a committee, we automatically know that we're working with a combination. Okay, combination. Okay, so let's read through this one. A committee consists of 7 seniors, or sorry, a group of people a committee consists of 3 people. Let me slow down. And we're going to select those people from 7 seniors, 5 juniors, and 3 sophomores. Okay? And we want to know the probability that a committee consists of all seniors. So anytime you're looking at probability, like that's the question that you're being asked, you're going to have something where you're dividing 2 different features to find that. Okay? The top is going to be what you want to have happen. right? And the bottom is going to be what all ways are possible for something to happen. So in our example, what we want to have happen is having all seniors, right? So on the top, I want the number of ways of getting all seniors, which we'll have to calculate in a moment. But on the bottom, I want the number of ways of getting any group, right? The number of anything happening. So we're going to get these two features, and then we're going to come back up to this as our thing that we're going to do to calculate it. So we're kind of like doing the last problem in reverse. We started by writing down what we want to do in part C, and then we're going to go back to parts A and B and actually find those pieces to divide. Are you with me? So I bring this up because some of your problems are structured just like this. They start out by asking this sort of broad question, and you've got to do some preliminary steps to get there, and that's where we are. So we need to know the number of ways of getting all seniors. So we'll start with that one just because it's on top. So how many seniors are there? 7. We said it's a combination. And how many are going to be how many would we need to create a committee? 3. It said committees are 3 for what we're looking for. So this is 7C3. So the 7 goes on top. The denominator is both the number I'm choosing and the number I'm not choosing. So I'm choosing 3. How many am I not choosing? 4. So I'm going to write my 7 down till 4. I'm going to write my 3, 2, 1. So the 4's cancel. What else? Yeah, the 3 and the 2 make 6. All that leaves me with is 7 and 5. And 7 times 5 is 35. Okay, is that good? So there's 35 different committees that could be made that are all seniors. That's what that says. But we also need to find the denominator part, which is the number of ways of making any committee of any group of students. Okay, well, how many students do we have to pick from? Is it 15? Okay, so we have 15 students to select from among, and how many are we picking? 3. So I have my 15 factorial on top now. 3 factorial, how many I'm picking on bottom? How many am I not picking? 12 factorial. So I have 15, 14, 13, and 12 factorial over my 12 factorial. And I'm still selecting 3, so it's 3, 2, 1. My 3 factorials, or my 12 factorials cancel. What else? 3 and 15 will give me a 5. 2 and 14 will give me a 7. So we have 5 times 7 times 13. $455. So we take these values now and go back up and actually answer the question we were asked. I have 35 on top. I have 455 on bottom. If you want to keep it in fractions and simplify the fractions, that's totally cool. I think for the purposes of interpretation, decimals might be a little bit easier to interpret with what's going on here, so that's the way I'm going to write mine down. Go ahead and grab a calculator and do the division, and we'll write things to 4 decimal places when we're doing this. What do you get for this probability? 0.0769. Okay. Again, if you multiply that by 100, you'd get about 7.7%. Right? It's not very high. It's not very likely. It's less than 10%, right? It's a less than 10% chance that this is going to happen. But it's not like 0.05% on the last problem, right? Okay. B is actually able to use part of our information from A. My question changes to being, what is the probability the committee has no seniors? So this means I need the number of ways of getting no seniors divided by the number of ways of getting anything. But we already know one of those. What do we know? We know the any group. How many was it? 455. So don't do the work twice, right? My daughter's doing long multiplication right now in some of her homework stuffs. And when she multiplies by something like 44, we're trying to show her if she's already multiplied by the 4 in the 4 spot, she doesn't really have to redo all the multiplication and multiply by 40, right? You just take the same numbers and you shift them. You don't have to really redo it. So don't redo work. Pay attention to what you're finding. So the only thing that we need to actually find here is the number of ways of getting no seniors. So getting no seniors means I'm only getting juniors and sophomores because there's no freshmen in my problem. So how many juniors and sophomores are there? 8. And how many am I choosing? 3. Committee's still 3 people. So I have 8 factorial on top. I'm choosing 3. How many am I not choosing? 5. So we'll write our 8 down to 5. And I have 3, 2, 1, and 5 factorial. 5's cancel. What else? 3 and the 2 make 6. So I'm left with 8 times 7, which is 56. So that's the numerator I needed above. And again, grab your calculator. It's going to be bigger than the other one because the numerator's bigger. Denominators are the same, right? What do we get for the likelihood of this one as a decimal? 4 decimal places. 0.1231. So slightly more than a 10% chance, 12.3 or so. Now, you might be thinking, well, wait a minute. Wasn't that all my options? And the answer is no. Most of your committees are going to include some seniors and some not seniors. That's what's missing right now. You could actually answer the question here of how many committees contain some but not all seniors. You could just take the number 1 and take off the pieces that we just found, and it would be the rest of them. Now, we're not asked to do that, but realize that the likelihood is in this committee structure, somebody is going to be a senior is going to be on that committee.